Hi, I'm Yogev from Tel Aviv University. This is a joint work with Yishay and Mansour on optimal publishing strategies on a base layer. So the problem we're tackling in this research is that many products nowadays require periodic interaction with the blockchain. This includes pricing oracles, for example, that need to update pricing pretty frequently on the blockchain, or layer 2 solutions like rollups that need to finalize their transactions on the layer 1 blockchain. The problem with this is that the gas price of the layer 1 blockchain might be very expensive in certain times and less expensive in later times. So it might be worthwhile to just wait with publishing your transactions and wait for a cheaper price to publish. However, this may incur a delay cost because sometimes you need to be very updated, and publishing on a later time might be also expensive. So for example, for pricing oracles, it's very expensive to wait for publishing because the prices need to be very updated. For rollups, it's less expensive to wait, but uh, they still need to publish on the layer one blockchain pretty frequently, so the layer two transactions would be finalized. So the question we're asking is how can we balance this trade-off, and what is the optimal policy to decide whether to publish your transactions or whether to wait for a later time where the gas price is cheaper, and what are the properties of such policy? Model this problem is sort of a Markov decision problem, where at each time step we are presented with the new transactions that we want to publish on the base chain, and then we need to choose whether to publish it in the past transactions we didn't publish it, or just wait and for a lower gas price and for a future time step. So we denote the gas price as PT, as you can see, and we assume it's distributed randomly according to some random function R. So PT plus 1 equals R of PT. And the cost that we incur at step T is divided to two costs, basically. So the first one, as you can see, CTP is the publishing cost, which is in gas units. How much is it to publish the transactions that we want? Um, and CTD, which is the delay cost, which is um, how much will we pay to wait for a future transaction with the transactions that we choose not to publish at this timestamp. The total expected cost is the discounted cost of the discounted total cost of all the costs we incurred during all time steps. And our goal in finding the optimal policy is to find a policy that basically minimizes this cost, um, or at least identify how this policy should look like. Investigating the first case where the publishing cost is constant, which means that no matter the amount of information we have that we want to publish on the layer one blockchain, we always pay the same price in gas units. So this is relevant in cases where you only need to publish a hash of the information you have, or for example, publishing a Merkle word of the layer two transactions, stuff like that. So it's very easy to notice that if the cost is constant, then we should always publish all of the transactions we have or nothing. Because if we publish one or publish 100, it's the same cost. So it's better to just publish everything. And I mean, if you only have one transaction that you need to publish, better to just publish everything and it would cost the same. So the only question remains is how we can decide whether to publish all of our transactions or wait with all of them. So the first thing you notice is because we always publish all or nothing, the delay cost is now determined only by the less time that we published, and not by which transactions we published. So we can define a new term which we denote by FD, which is the aggregate delay cost, which is basically the aggregate delay cost between the between two publication steps. So FD of n is how much delay cost we incurred by waiting n steps between two publications. Now, if the gas price is also constant, so PD is always equal to P for some constant P, we can show that the optimal policy is to just publish in constant intervals of the size you can see on screen. So this is pretty intuitive because if everything is constant, you just need to wait until you have enough transactions that justify the cost to publish, and then you publish, which is a constant interval always. So taking this into account and taking a linear delay cost as an example, which is how we like to model roll-up chains, the delay cost of roll-up chains, we can see that the aggregated delay cost we incur between two publications is about beta times p, where beta is the price to publish on the blockchain. So beta p is also the actual price, not in gas units, the actual price we pay when we publish on the blockchain. So we actually got that the delay cost for the optimal policy is always equal or about the same as the publication cost. This makes us think maybe we can generalize this idea that we should maintain the delay cost to be about the same as the publishing cost and choose our publishing steps according to this rule. So now we defined a new condition on the aggregated delay cost, which is sigma subadditivity. You can see on screen the formula that defines it. Basically, what it means is that if we remove a time step, a publication time step between two publications, then the aggregated delay cost is not so much worse than it was when we had the publications step in the middle. So removing the publication step doesn't affect the delay cost too much, not by a factor of sigma. So we show when this is true for aggregated delay costs, and by the way, it is true for the linear delay cost, we talked about it earlier, then it is near optimal to publish when the aggregated delay cost is larger than the publication cost of the current time step. So basically, we try to maintain the delay cost and the publication cost about the same, and we prove that this is near optimal. When we say near optimal, we mean that the total cost of this policy is at a worst case times sigma more than the real optimal policy. So we showed what is the optimal policy for the constant publishing cost. Now we look at the homogeneous publishing cost, which means basically that the gas cost is linear in the amount of information that we have to publish. Or as we can see on screen, if we have n transactions, we're gonna pay alpha times n. So alpha gas units for each transaction we have to publish. Before we get into how the optimal policy looks like in this case, let's define what is a nicely behaved price fluctuation. So the first condition for a nicely behaved price fluctuation is that it is monotonically increasing. This is fairly intuitive. What it basically means is if we have two different cases where one have price P1 and the other has price P2, and P2 is larger than P1, then we also expect the next time step so to be higher in after P2 rather than after P1. So RP2 is larger than RP1 if P2 is larger than P1. This is fairly intuitive. The other condition is that the prices are non-expansive. So we can see the equation for it is the difference between the expected price of the next step is lower than the difference of the prices in the current step. The intuition behind it is that the prices tend to approach a certain value if you give them enough time. So we can show in this work that if the price fluctuations behave nicely and we have a homogeneous publishing cost, then the optimal policy is actually a threshold policy. So what it basically means is that the policy is that for each transaction we have some kind of threshold that depends on the amount of time that has passed since we got this transaction, and and once the price is lower than this threshold, then we need to publish. And as long as the price is higher than this threshold, then we don't publish this transaction. So to see that our assumptions on the gas price fluctuations actually hold in real life, we took data from 2 million Ethereum blocks, and we actually see that the distribution of the base fee in Ethereum is distributed log normally, which means the logarithm of this distribution is a normal distribution. So this function, the log normal function, is actually nicely behaved. So we can use our results for Ethereum gas prices. Okay, we have a sense now of what is the optimal policy for homogeneous publishing cost. Now let's look at how this actually looks like in a real scenario using a linear delay cost, which is how we model rollups. So we can see we get a pretty complicated equation for the price threshold, which is actually not a closed equation, which basically means let's compute the predicted price we're going to pay for publishing for each future time step and take the minimal one. And if it's less than that, then we should publish now. If it's more, if the current price is more than that, then we should wait for this future time step. So this is a fairly complicated equation, but it actually turns out to be real nice where the gas price is martingale. This basically means that the gas price in the next time step is expected to be the same as the current gas price, which is a common assumption in finance. In this case, we get a simple solution that the price threshold is linearly dependent on the delay and inversely linearly dependent in 1 minus gamma, where gamma is the discount factor. This is very intuitive because we can understand that the longer we wait, uh, we we want to publish more quickly, because if we waited too long, then now the delay cost is very high. But also, if the discount factor is very large, then we also we have no reason to wait, because we expect the next gas price to be the same as now. We don't expect the discount factor to have much implication on how much we pay. So there's no reason to not publish just now. So if you take, for example, gamma equals 1, we get an infinite threshold, and we just always need to publish with if we have no discount. But if the discount factor is very small, so for example, if we wait even one time step, then the publishing cost is much lower for us. Then of course we're gonna want to wait for the next time step. Here we show a simple simulation we did where we simulated the price threshold policy we just showed in a simulated environment of a rollup, and we use the real gas prices from Ethereum we collected. The gas price fluctuations are shown in red in this graph, and in blue you can see the difference in the total cost between our policy and the trivial policy, which means just to publish whenever we get a transaction. So you can see our policy actually behaves much better, even empirically. All right, so that would be all. Thank you for your time.